Welcome to the Deep Dive. We're here to bring you the essential knowledge, the key insights from the latest technical research, really distilled into actionable intelligence. Today we're tackling a pretty significant tutorial paper, Robot Learning, coming from researchers at the University of Oxford and Hugging Face.
That's right. And our mission here is really to pull out the core shifts, the actual technical mechanisms that are pushing robotics, away from those classical models and into this new age of data-driven learning. And for you listening, whether you're an AI researcher or maybe an ML engineer, this deep dive should be a good shortcut to understanding what's next for robot policies.
Okay, great. Let's maybe crystallize this for the short form first, because there's a really clear story here, isn't there? We seem to be at a real inflection point in robotics, moving away from needing to meticulously model all the physics towards these huge data-driven approaches.
Absolutely. That's the crux of it. The transition from, let's call it explicit, dynamics-based control, where you try to write down precise equations for every movement, to implicit data-driven learning, where motion is treated more like a complex statistical pattern learned from data.
And this big shift seems to be powered by two main things. Loads of data and better tools.
Exactly. On one hand, we've got these massive open data sets emerging, things like OpenX, Droid, just huge collections of robot experience. And on the other hand, we have robust kind of production-ready ecosystems like lerobot to actually manage and use all that data effectively. And this whole environment has really let modern robot learning leverage, I'd say, three powerful ML techniques.
Okay, what are they?
So first, there's sample-efficient reinforcement learning. A key example is hill searle, which drastically cuts down how much real-world trial and error a robot leads. Second, generative models. Things like Diffusion Policy, ACT, they're tackling this really tricky problem of how to learn from human demonstrations when humans do things in slightly different, valid ways, multimodality.
Right, the multimodality issue. And the third big pillar, generalization.
Absolutely. That's the move towards large-scale vision language action models, VLAs. Think models like PIO-LOLR or small VLA. The goal here is policies that aren't just good at one task, but are truly generalist. And crucially, their performance scales up the more data you feed them. So the fundamental insight really is shifting away from these brittle, explicit models towards unified systems that go straight from perception to action.
Okay, that sets the stage perfectly. Now, to really grasp why this learning approach is so promising, we probably need to dig into why the old way, the classical dynamics-based method, is kind of running out of steam.
Yeah, you have to look at the inherent limits when you rely only on explicit models. Classical robotics is built on kinematics and dynamics, FK, IK, differential IK. It basically means every single action needs a precise, calculated equation of motion. Learning-based methods, they swap this out for implicit modeling learned from data.
And the paper points out, I think, 4 big problems when you chain together all these explicit modules. What's the main sort of headache?
I'd say the biggest one is the integration challenge. Classical systems are pipelines, right? Sensing feeds state estimation, that feeds planning, which then feeds control. Now, if you have even a tiny error early on, say in sensing, that error just gets bigger and bigger as it goes down the line. By the time you get to actually telling the motor what to do, the command could be completely off.
It's like that assembly line analogy, isn't it? If you're off by a fraction at the start, the end product is just wrong.
Precisely. Then there's the multimodality challenge. Classical methods really struggle with raw, high-dimensional data streams like RGB video, depth data, gyroscope readings, all coming in at once. You end up needing extensive custom feature engineering for basically every single sensor input. It just doesn't scale well.
Right. You're essentially handcrafting how the system should interpret every bit of new data.
Which connects to the third point, the undermodeling issue. This one's maybe the most practical limit. Think about complex, real-world stuff like friction or contact physics or how to handle something soft and squishy. Classical methods force you to simplify these complex things into neat analytical models. But those simplifications are often just not realistic enough, which really limits where you can use these robots.
Yeah, friction is always the example that comes to mind. It's the difference between a robot in a pristine lab picking up a perfectly known block, and that same robot trying to grab, a wet bar of soap in a real kitchen. Almost impossible to model perfectly beforehand.
It really is. And maybe the final sort of overarching constraint is that these classical methods just aren't set up to take advantage of this explosion in large, diverse, open robotics datasets, which is arguably the single biggest trend driving AI right now. The learning approach, on the other hand, promises this unified pipeline, automatic feature extraction, less dependency on perfect dynamics models, and performance that just gets better with more data.
Okay, so that leads us directly into reinforcement learning. If modeling the dynamics is too hard, why not just let the agent figure out the policy, the Doubt-you-are, by trying to maximize its reward over time? You basically bypass needing that explicit dynamics model altogether.
Yeah, it's an elegant idea. But the moment you try to do RL training purely in the real world, you slam into the reality gap. And safety issues, of course. Simulations are just too clean, too predictable. A policy trained only in sim often breaks when it meets messy, real-world physics.
And the traditional workaround for that is domain randomization, DRUR. You basically jiggle parameters in the simulation, fiction, lighting, textures to try and force the policy to be more robust.
DR definitely helps, but it often just introduces a different kind of manual effort. You, the human, have to decide which parameters to randomize and how much to randomize them, defining that distribution in Calatory. It's still relying on specialized human guesswork, which is why the field's focus has really shifted towards highly sample-efficient RL, trained directly in the real world, but smartly guided by existing data.
Okay, now we're getting into the technical meat. Let's talk about Hill-Searle, human-in-the-loop, sample-efficient RL. The paper presents this as sort of a combination of the best recent ideas to crack this sample efficiency nut.
Hill-Searle is really interesting because it bundles several clever solutions together. First, it uses what they call an offline to online learning setup, sometimes called RLPD. It doesn't just start learning from zero. Its replay buffer maintains a mix, maybe 50-50, of high-quality offline data like expert demonstrations and new online data the robot collects itself.
So you're bootstrapping the robot with some good examples. Its initial exploration isn't just random flailing, it's already guided towards useful behaviors.
Exactly. Second big idea. It gets around how incredibly hard it is to design a good, dense reward function, telling the robot exactly how well it's doing at every tiny step. Instead, it uses a learned reward classifier. A human provides examples of successful end states and failure states. The system then trains a classifier to basically say, based on what I see right now, does this look like a success state or not? That becomes the reward signal.
That seems like a huge simplification. Instead of needing a complex function saying, you get 0.8 reward because you move 2 centimeters closer, it's just, yep, looks like success, or nope, looks like failure.
Precisely. Much easier to provide that kind of supervision. And the third innovation is more about speed and efficient hardware use, a decoupled architecture. They actually split the system into two parts, an actor and a learner. The actor is the part that runs on the robot, interacts with the world, collects data using a policy that's currently frozen. The learner is separate, maybe running on a powerful GPU server somewhere else. It takes the data collected by the actor and does the heavy lifting, optimizing the policy parameters. Then it sends the updated policy back to the actor.
Okay, what's the real practical win from splitting those two jobs up?
Well, they communicate using queues. And the crucial part is that the computationally expensive bit, the learner doing all the optimization, can run on serious hardware, maybe even over a network. Meanwhile, the actor running the robot can be on a much lighter local machine. This setup allows for massively parallel training. You can have multiple actors collecting data, feeding a central learner. It really boosts throughput without slowing down the robot's real-time control.
And the bottom line result is pretty impressive, right? Hill-Searle gets these incredibly high success rates, like 99% plus, on tricky real-world tasks in just, 1 or 2 hours of actual robot training time?
Yeah, it's transformative. It makes real-world RL actually seem feasible for complex tasks. It really demonstrates that guiding the exploration with prior data and human feedback is just way, way more efficient than purely random exploration.
Makes sense. But even with something as efficient as Hill-Searle, there must be situations where any online exploration is just too risky or too expensive. Or maybe labeling success-failure states is too hard, which I guess pushes us towards pure imitation learning.
Exactly. Imitation learning or behavioral cloning, BC, is often the pragmatic choice. Just learn the mapping directly from observations to actions, $5. Right away, using a dataset of expert demonstrations, $. The challenge, though, isn't just learning any mapping. It's learning one that actually works reliably.
And the big pitfall for simple supervised BC is this multimodality crisis they talk about.
Yeah. Imagine teaching a robot to grasp, say, a hammer. A human might demonstrate 2 perfectly good ways to grab it, maybe symmetrical grasps. Simple BC, like a standard regression model, tries to find the average of those 2 valid grasps.
Which means the action it predicts is somewhere in the middle. A point where there's no valid grasp at all. So it hesitates or just fails.
Exactly. It averages across the different modes of good behavior, leading to useless or unsafe actions. Plus, standard BC is notoriously bad with compounding errors, what's called covariate shift. A tiny mistake in action at time mark pushes the robot slightly off the path the expert demonstrated. So the observation at time +1 looks unfamiliar, it's out of distribution, the policy makes another, potentially bigger error, and things can quickly spiral out of control.
Okay, so generative models enter the picture here. They're the solution because they don't just predict the single best action, they try to model the whole underlying probability distribution, POU. They can actually capture all the different valid ways the expert might act in a given situation.
Precisely. And we see this implemented in a couple of key ways. First, there's action chunking with transformers, or ACT. This often uses something like a conditional VAE architecture, but the really core idea is that instead of predicting just the very next action, it predicts a whole sequence or chunk of future actions, ADD plus HA.
And why is predicting a chunk better for dealing with those compounding errors?
Well, when you predict a whole sequence, you're forcing the policy to think a little bit further ahead, to plan a short trajectory. It inherently builds in some temporal smoothness and consistency. It reduces the chance that the very next tiny action accidentally pushes the robot into some weird, unseen state where the policy has no idea what to do.
Makes sense. Okay, next up, diffusion policy, DP. This applies diffusion models, which have been huge in image generation to robot control.
Right. TP learns the action distribution by training a model to gradually denoise a randomly generated action chunk, conditioning the denoising process on the robot's recent observations. These models are known to be really good, very robust, capturing complex, potentially multimodal distributions. And importantly for robotics, people have developed faster sampling techniques like D-dim denoising diffusion implicit models, which can speed up inference, getting that action chunk prediction maybe 10 times faster than the original diffusion process, which is critical for real-time control.
But the paper also highlights an even perhaps more efficient and stable approach, flow matching. FM.
Yeah, flow matching is interesting. You can think of it as related to diffusion models, maybe a generalization, but instead of learning that step-by-step denoising process, it learns to predict a continuous, deterministic flow, like a vector field that smoothly transforms a simple noise distribution into the complex action distribution. Maybe an analogy helps. Diffusion is like modeling how raindrops scatter in a storm. Flow matching is like modeling the smooth, continuous current of the river itself.
That's a great way to put it. So, modeling the smooth flow instead of noisy steps. That means flow matching is more sample efficient during training. And crucially, faster at inference time because it's deterministic, not stochastic.
Exactly. You get the power to model multimodality like other generative models, but potentially with better training stability and the fast inference speed needed for robots reacting in real time.
Okay, so now we have the building blocks. Sample efficient RL, like Hill-Searle, for learning from interaction, and robust generative policies like ACT, DP, or FM for learning from demonstration, especially handling multimodality and compounding errors. The next logical step is scaling up, right? Trying to build policies that aren't just task-specific, but can generalize. This leads us to Vision Language Action Models, VLAs.
Yeah, and this addresses a historical bottleneck in robotics, data fragmentation. Unlike computer vision or NLP with their massive unified datasets, robotics has traditionally had lots of small, isolated datasets specific to one robot or one task. That's been changing.
Right, because of these big aggregation efforts. You mentioned OpenX earlier, 1.4 million trajectories across something like 22 different robot types. And Droid, with over 75,000 demos collected in the wild, this is the fuel needed for generalization.
Absolutely. And VLA models, like RT2 or the $10 model detailed in the paper, aim to leverage this data by building on top of powerful pre-trained vision language models, VLMs, the kind that power things like ChatGPT with vision. They essentially frame the robot control problem as a kind of visual question-answering task. The input is the camera view and maybe a language command, and the output, encoded in the same language space, is the robot's action.
Let's dig into $P specifically, since the paper presents it as state-of-the-art. It seems focused on both generalization and being compute efficient. How does it achieve that?
It uses a clever mixture of experts' MOE architecture. It basically combines a very large, powerful VLM backbone, say, Gemma 2.6 billion parameters, which is great at understanding the visual scene and language instructions, with a much smaller specialized action expert. This smaller expert is solely focused on outputting the precise continuous control commands for the robot.
Okay, a big brain for understanding, a smaller, focused module for acting. How do they make sure these two parts work together effectively without messing each other up?
That's where this blockwise causal attention masking comes in. It's a really key architectural detail. During the fine-tuning phase on robot data, they deliberately prevent the big VLM backbone, which was pre-trained on vast amounts of web text and images, from paying attention to the robot-specific inputs, like joint angles, proprioception, and the action tokens themselves.
Why is that masking so important? What's the risk if the big VLM does look at the low-level robot data during fine-tuning?
The risk is essentially polluting the VLM's hard-won general world knowledge. The VLM understands concepts like pick up the red block. The action expert deals with things like set joint 3 velocity to 0.5 radians per second. If you constantly backpropagate gradients related to precise motor control through the entire giant VLM, you risk confusing its high-level semantic understanding, potentially degrading its ability to generalize to new situations or instructions. The masking insulates the VLM's general knowledge.
That makes total sense. You preserve the world knowledge in the big model while letting the specialist handle the motor skills. And the actual control output from that action expert uses flow matching on action chunks, right? Giving that fast, reliable, multimodal prediction we talked about.
Exactly. And Paspadollar trained this way demonstrates really impressive cross-robot generalization. It can even handle different robot setups, like varying numbers of cameras or different joint configurations, using simple techniques like padding the input tokens.
Of course, none of this scaling up, none of these huge data sets or complex models would be practical without some serious work on infrastructure and standardization.
Which brings us to lerobot and the lerobot dataset format.
Yes, lerobot dataset is absolutely critical. It's a standardization effort to finding a common, efficient way to store and access robotics data. It breaks data down into 3 main parts. You have tabular data for things like joint states, velocities, actions, low-dimensional, often high-frequency stuff stored efficiently in memory-mapped files. Then visual data, where camera frames are grouped together and encoded into standard MP4 video files, which is much more efficient than storing millions of individual image files. And finally, metadata in JSON files, describing the data structure, statistics, where episodes begin and end, and so on.
And you mentioned efficiency. Why is merging data from multiple episodes into single, larger files important? It's all about reducing I/O overhead, especially when dealing with massive data sets potentially stored in the cloud, like on the Hugging Face Hub. Opening and closing millions of tiny files is incredibly slow and puts huge stress on the file system. Having fewer, larger files makes streaming data much, much faster and more efficient. This is essential for training models on datasets like OpenX.
Okay, standard data format solved, but what about the inference latency? These policies, like $10 predict chunks of actions. Doesn't calculating that chunk take some time, potentially making the robot pause?
It can, yes. And that's where optimized inference, or async inference, comes in. It's another clever decoupling trick. It separates the robot client, which is running on a robot and actually executing the actions, from the policy server, which is doing the potentially heavy computation to predict the next action chunk. The robot client executes actions from a queue.
How does it know when to ask for the next chunk without stopping?
It monitors the queue. When the number of actions left in its queue drops below a certain threshold, say $555, meaning half the chunk is done, then it sends the latest observation to the policy server and requests the next chunk. The key is that the policy server starts computing the next chunk while the robot client is still busy executing the remainder of the current chunk.
I see. So you're overlapping the computation time with the execution time. Instead of execute chunk, wait for next chunk, execute chunk, it's more like execute chunk A, start requesting B, finish A, receive B, execute chunk B, start requesting C. You hide the latency.
Precisely. It avoids that dead time waiting for the policy inference and keeps the robot moving smoothly and reactively. It also means the heavy policy server could be running on a powerful remote GPU while the robot client stays lightweight. It really completes the picture of an optimized end-to-end stack for modern robot learning.
Okay, wow. We've really covered a lot of ground here. From the fundamental limits of classical dynamics modeling, all the way to these generalist VLA policies using techniques like flow matching in architectures like $2, and underpinned by essential infrastructure like lerobot.
Yeah, and I think for you listening, if you're an AI researcher or an ML engineer, the big takeaway here is accessibility. The barrier to entry is significantly lower now, with standardized dataset formats like lerobot dataset and powerful open source models becoming available like OpenVLA, small VLA, potentially Diffusion itself. The ability to actually develop, train, and experiment with these highly capable generalist robot policies is becoming much more widespread.
It really feels like a paradigm shift, doesn't it? where robot capability becomes less about painstaking physics modeling and more about the scale and diversity of the data you can train on. And if we sort of extrapolate that trend, models getting more compute efficient, maybe smaller, like small VLA, while the data sets become vast, open, and decentralized, it raises a pretty interesting question, right? What happens when the sheer volume of this collective global robot experience captured in these data sets gets so large and diverse that for many real-world tasks, we can actually just skip the high-fidelity simulator stage altogether?
That's a fascinating thought. If that happens, the core focus of robotics research might fundamentally change. Instead of spending years trying to perfectly model friction or contact dynamics, the primary challenge could become how to best curate, manage, integrate, and fine-tune models on these enormous streams of real-world experiential data. The future might really be about harnessing experience rather than just modeling physics.
A truly fascinating prospect for the next few years in AI and robotics. Well, thank you for joining us on this deep dive into robot learning.
My pleasure. Always fascinating stuff.